So, this week we will be talking about Pd and Pi controller, additionally to the P-type controller. Now, we have a system, segment system, where the zeta and omega n values are given. And then we've also now the overshoot. So last time we had the settling time requirement for the design. Now we will be focusing on the overshoot. Here we have a 10% overshoot requirement. And you'll see the formula here. So let me zoom in. Now, note that I've written it a bit different than what you might expect. Namely, we might use the log n or ln in short. Now here I've provided log on base e. The reason for that is the following. I will use it on MATLAB. And in MATLAB, when you use log, it is by default the natural log. So if you take the log of e, you will get 1. If you want to use the log 10 or log 2, there are functions called log 2 and log 10. So if I provide 10, I again get 1. So to not confuse you, I've changed the notation here. So if you're using a calculator, please be sure that you're using the natural log here. So now, and most of the time you see the inverse formula here, which is an exponential formula, e to the power of minus p zeta divided by and so on. Here we have the inverse relation. The reason for that is the following. We don't want to calculate the overshoot that's corresponding to zeta. We're trying to work our way out for the zeta value that is necessary when we have a given preset overshoot value. So we want to plug in the overshoot. We want to get the zeta value as a result, because that will be one of our design parameters in this case. And today we will try to design P-type, Pd type, and Pi type controllers. So as usual, P-type controller will not be that much of a struggle, but here in Pd type and Pi type controller, I have to note that they have additional parameters. Therefore, we'll see what that will affect. So let's quickly start with the first part, because we know what and how to design a P-type controller. So here we are given the overshoot value, but before that we have also again zeta equals 1 and omega n equals 2, if I'm not wrong. Exactly. Now let's define our open loop transfer function here. That looks like this. S squared plus 2 times zeta times omega n times s plus omega n squared. Now I'm going to quickly also define the transfer function object here, omega n squared, comma 2 times zeta times omega n, and then again omega n squared. Now you can see, instead of giving the transfer function itself directly, it is given indirectly by defining the zeta and omega n values here. In the previous weeks, we've talked about this. If you have a zeta value, if you have an omega n value, that corresponds to a complex conjugate pole pair. Or in other words, it corresponds to a second order transfer function without a zero. Now I've added this omega n squared for the fact that if you plug in s equals 0 here, for example, you can immediately see that the gain will be equal to 1. So this means that if I apply a step input to this transfer function and look at the step response, I'll get a gain of 1. So if I'm using a unit step, then the output should settle down to 1. So that's here important to know. Because if that's not the case, then the gain would be 1 divided by omega n squared, for example, if the numerator here is equal to 1. So, and you can also see that we've used zeta and omega n to define our second order transfer function, but again, using the overshoot, which is 10% here, we will get a different zeta value. So that's kind of implying that we are trying to change the behavior of the system, because we've talked about the zeta value, and we've seen that the zeta value kind of describes the system's behavior in terms of transients, which also means that the overshoot is determined by zeta. So now we have a certain overshoot that's 10%. So let me define that, 10 divided by 100. Now I'm going to use the minus log overshoot divided by the square root of pi squared plus log overshoot squared. So let's see. Now our value is 0.5912. So if we have such a zeta value, then the overshoot should be equal to 10%, no matter what omega n is, because the overshoot is directly affected by the zeta value. So now we know what the zeta value should be, and we have a second order transfer function. So if we would have known what the omega n value should be, for example, via the settling time or something else, then we would be directly constructing the closed loop characteristic polynomial or even the transfer function that we're looking for. But that's not the case here. So therefore, I'm going to define omega n as a symbolic variable. And then I know that my desired polynomial should look like 2 times s squared plus 2 times zeta times omega n times s plus omega n squared. Now I have to also work out what the closed loop actually looks like. So let's define K. And since we've defined GSS, we can get K times GSS divided by 1 plus K times GSS. Now let's extract the numerator and denominator here. And then we're looking for the denominator here. So that's basically given, and we constructed PDS here. So in order to see it better, let me use VPA here. So by directly looking at these two polynomials, I can see that I have 1.182 times omega n here. But in the actual system connection, I can see that there's a 4 here. And we've also omega n squared here, but there's 4k plus 4. So let me first state the problem itself, the actual problem here. The problem is to equate the coefficients of the denominator of the resulting closed loop to the coefficients of PDS. Let me use also a for loop here in order to cycle through each equality here in the problem. So let's display VPA problem ith element. And we should be good to go. So now, here we can see that the first equation is the trivial equation, but it's also important to check this equation, the first equation, which is the highest order S term in this case, because if these are not equal to each other, then we are not able to solve it. Even in MATLAB, if you solve on this, since that would be a false identity, it will give you an empty solution. So we have to check this. This is basically a necessity equation here. And it might be the case that that's not equal to 1. And the reason for that would be the following. For example, let me plug in 2 times s squared here. So if I run it again, let me see, GSS, PDS, yeah, that should be no problem. So GSS, So 4 times this, okay. Now TSS. Let's simplify this. Interesting. So we have PDS, we take the coefficients. The denominator looks like this. Interesting. Normalde buradan 2 gelmesi lazım şu an. Şöyle bir şey deneyelim. Enteresan. Şimdi geldi. Omegen 2 olduğu için mi olmadı? Bir daha bakalım. Galiba sadeleştirdi öyle olunca. Neyse. Now, for some reason, if we use omega squared due to maybe 2, let me also change this to 3. Maybe that's the case. Let's see. Yeah, of course. Now, since we've used 2, it directly gets rid of that because they cancel each other out. So that was the issue there. Now, if we have a different value than, for example, 1, if we have 3 here, you can see that the coefficients on the left have 3 in it. So we're basically taking this coefficient and then the S term and then the constant term, and that's the left-hand side of this equation. So if we have 3 equals 1, I'm not going to be able to solve this. So if you want to be a bit safer than this, what you can do is you can go ahead and take, since this is in the denominator here, you can take an extra step here to calculate the coefficients of then here. And then what we can do is we can go ahead and normalize this. So I'm going to take the first coefficient in this polynomial vector, because if I take the coefficients here, 3, 4, and 4k plus 4 would be the coefficients here. And the first one of them is the highest order term coefficient, 3. So I'm going to divide everything into 3 here. So then I would get 1 equals 1. Since the right-hand side is the constructed polynomial coefficients, I can basically safely assume that I've used the correct values. Another version would be to use the coefficient. Let me fix this here. I could also include the coefficient here. If it's 3 times s squared, I can add it manually here. That's also possible, but it would be a better option to normalize the left-hand side or to normalize the actual characteristic polynomial. So let's again check, and you can see now if I use 3 there, it directly divides all the coefficients on the left into 3, and we have 1 equals 1. So this is a necessary equation, but also a trivial one. If that's 1 equals 1, then it has no meaning, but it should be 1 equals 1. So let me get rid of this again. Even though this was not the case, we might be a bit safer. So now looking at this set of equations, I can directly conclude that omega n has a certain value, namely 4 divided by 1.182. So at the beginning, I didn't know what omega n looked like, but it turns out that the connection itself has already a limited ability for this coefficient. So I can only choose omega n according to this equation. So that arose naturally in this case. Now, if I'm going to calculate omega n from here, what I can do is I can directly plug it into this equation, and I can conclude what k should be. So this shows me that there is a certain limitation on the system. I can maybe decide on the overshoot value, because I can change this here. And that would give me zeta, and I'm going to adjust the value there. But I cannot also change omega n for this system. because my coefficient only affects the constant term. So therefore, the S term here, for example, should be restricted to the system coefficients or this equation here. So now let's call the solve function. So solve the problem. And we will have omega n and k values here. Of course, we might convert them into doubles. So omega n val equals double, and then this. So we have values here, 1.8615 for k and also omega n. So at this point, I have calculated a k value here. So what I have to do is I have to verify the results. I have designed or synthesized the controller, but I should check out the closed loop, apply a step function to it, and see what the output would be. So let's use feedback, and then k-val times gs, 1. And let us construct a figure here. So I'm going to plot the root locus and the closed loop step. So therefore, they'll be side by side. I'm creating a subplot here. So let's calculate what the step response looks like. Of course, we can also change the title here. Step response. But again, as I've mentioned, I'm going to look for the root locus. So R locus and then GS. Now, since I'm going to plot the root locus plot, what I might do also is to calculate the closed loop poles and zeros if there are any. So let's use pzmap, provide TS, and let's use the plot function here and plot the poles. Because these exact locations would be my solution on the root locus, so they should be on the root locus plot, and we'll see if there are. There we go. Now, so now we can see that the step response is given on the left, and we have a root locus plot on the right, but I cannot see where the poles are. So that could be because of the reason that the root locus has its own limits, and we are maybe zoomed in a little bit. So what we might need to do is zoom out, and we can see now they appear. So that's good, at least. So it seems like I have to adjust the Y limits here by default. So let's do that. So let me see what omega n val was looking like. Okay, it's 3.38. So we can use ylim here for ax2 and provide the limits manually. For example, -5 and 5 looks like it should be working. So let's try it again. There we go. Now we have this zoom out. So let's also calculate the overshoot here, because I can use step info for that, and it will give me the overshoot value here, because I can of course use the tools here and try to read it and calculate it myself, but why not use MATLAB? And what I can also do is I can also plot the omega n values here and zeta values here in order to ensure that this exact point corresponds to the point that I'm looking for. So therefore, we can use sgrid here, and sgrid expects us to provide the zeta values here and omega n values here. So that's one thing. And here I can go ahead and look for the step info of TS of the closed loop, and then maybe use, so let me change it a little bit. I can use something called display name here. And in this display name, I can provide something that will be then shown on the legend here. If I say show, that's going to show this message for this plot here. Now you can use a legend function on its own. You can just have multiple plots here and provide multiple arguments here, but you can also assign some display names to each plot. And even if you change the order of the plots, you don't have to update your legend function. Therefore, this might be a bit safer or better for use. Now, let's display the overshoot value in the legend here. So what I can do is I can use the string function here in order to convert numerical value into string and directly call overshoot here. So this will basically take the value, turn it into a string, append it to this string, and display it as display name. Okay. So now we can see what the value is, and we have also these omega n and zeta plots here. Now we have chosen a certain omega n value, which was 0.591. So we're on that line here. And we have also the omega n value, which is 3.38. And if I multiply them, I will get this exact point. Now here we can also see that the overshoot value is as expected. That's also nice. But what I can see for this system especially is that looking at the root locus, it reveals me the fact that I have no other choice than to choose a point that has this exact real value here. So if I, for example, change the omega n value, so the settling time of the system, if I try to change that, I'm not going to be able to do that. The only thing that I can decide on this closed loop system here is the overshoot itself. And the fact that the zeta values here can be chosen between 0 and 1, and it will correspond to a certain line here that will pass through this root locus here. That exact point would be my solution for that specific zeta value. So I can decide on zeta, but I have no other choice than take the real value here. Of course, the omega n value will change, because if you increase it, for example, a little bit, then the omega n value should be decreased, because the multiplication here is constant, because it gives me the real value, and the real coordinate of all the possible solutions with a P-type controller will be on this exact line with the same real value. So the P-type controller gives me the overshoot that I'm looking for, but you can also see that there is a steady state error because of the fact that the P-type controller settles down to this value here, which is 0.64, and I've applied 1. So there's a difference there. In order to decrease, at least, even if I'm not going to be able to get rid of it, I might decrease it a little bit. And for that, I have to increase the gain value. And the fact that I can do that is based on the following. We always use k times gs, or basically the transfer function, the closed loop transfer function looks like this. And in steady state, 1 plus k times gs. Now in steady state, I plug in s equals 0 into the transfer function. So in gs, if I plug in s equals 0, I'll get 1 for this specific case. So this gives me the following. gs is equal to 1. So then I'll end up in k divided by 1 plus k. Because k is a gain on its own, and gs in steady state is also a gain. Therefore, I'll end up in k divided by 1 plus k. Now, if I have a certain k value, then I can immediately see this will not be equal to 1. The only thing that I can do is to approach at least 1 is to increase k, because the greater k, the less significant becomes this 1 plus here. So therefore, I'll get closer and closer to 1. So, for example, if we use if I have 1, for example, then this corresponds to, of course, 0.5. But if I use 10, I can see that it is 0.909. And if I increase furthermore, I'll see that it is almost equal to 1. So therefore, what you can do is, if you are trying to decrease the steady state error, what you can do is you can go ahead and allow more overshoot. Now, for example, if I'm allowing 30% overshoot, which is more, I should end up in less steady state error. So let's see. There we go. We have a higher value here. It was 0.6, now it's 0.86. But the cost here is the overshoot, because if I want to increase k, since the root locus goes up in on this branch, I have to decrease the zeta value, which means that I should increase the overshoot value. So there's a cost there. Now, that's all I can achieve with a P-type controller. Let me again show the solution here. That's the best I can do here. It has exactly 10% overshoot as expected. I have a steady state error here. The root locus looks like this, and I'm stuck on this line. So the settling time, for example, cannot be changed with a P-type controller. So now, I've talked about this, and I've told you that, for example, in this case, I might go ahead and change my zeta value. So I can update my requirements. I can loosen them a little bit. That would offer me more solutions, hopefully. But another method is to update the controller or the structure of the controller. So Pd Controller, for example, will be the example for that. So I might go ahead and choose a different controller, which can be a Pd Type Controller. So what is a Pd Type Controller? Let me copy this far. I guess this is also necessary. And maybe this can be updated. So up to this point, we have used P-type controllers. Now let me introduce you to Pd Type controllers. Now, the more general form here is to use a transfer function instead of k. And using a P-type controller, what I'm actually doing is I'm choosing a gain, since I have a feedback loop, and in this feedback loop, there's a certain difference between the reference and the output called the error. And I'm taking a proportional part of this error and apply it to the system. So what if, for example, I can use also another data here, namely the derivative of the error. Now, this is a different controller. This is the Pde Type Controller. I have a proportional part. I've also a derivative part. Now, depending on the system, since we're dealing with dynamic systems, it will look on the changes of the error. So if it's, for example, an aggressive change in error, then I will apply a higher control signal to the system. So it will behave differently. Now, what I can also do is I can also use an integral part here. I can take the integral of the error itself. Now, this is basically the PID controller that I can use. And in this case, it is also important to note that this EDT integral part here is fairly crucial. And the reason for that is the following. What happens if E is a constant value? For example, E is equal to 1. So it's important to look at this, because if e does not change and is constant, then I can see that the integral here will be equal to dt, integral of dt, because e is equal to 1. Now then I'll get t, because that's the integral. Now, if t tends to infinity, then this value will also tend to infinity. And that's a bit problematic. So, of course, if I have a finite value, then this will also be finite. If I'm using an integral part in my controller, then ideally what I want to end up in is that the error should tend to 0. If error tends to 0, then this term will be constant, because 0 dt, that's constant. So the integral action here is fairly important, and we'll see. Now, of course, I'm going to go step by step. So therefore, let's take only the Pd controller. Now, if you use the Laplace transform, you can see that we will end up in k times e plus kd times. Since this is the derivative of e in the Laplace domain, I'm going to use s times e, and that's it. So let me also call this part kp, because we have multiple controller coefficients. So kp, the proportional part, kd, the derivative part. So now, since I have e as a common factor here, I can convert this into kp plus kd times s times e. So if I define the following transfer function, I'll end up in kp plus kds. And in line 19, u divided by e is actually the control signal divided by the error, which is fs. So the controller transfer function is kp plus kd times s. Now, the only thing that will change in terms of design, if you're using the polynomial coefficients method or the algebraic method, is the definition of your controller. You will always use the definition or the structure of the controller and calculate the closed loop transfer function, get the characteristic polynomial and its coefficients. And on the other side, you again need zeta and omega n values in order to determine your transients, and then you will construct the polynomial in order to be able to build the problem, which is the coefficient equation method. So let's define the controller here. I can directly do this like kp plus kds, but I can also use a different notation. Since we have, and let me change the order of these, kds plus kp. So since we have this kdkp here, what I can do is I can factor out kd here. I'll end up in this definition here. Now, here kp divided by kd is basically, or this whole term here is basically a polynomial. And if I multiply this with GSS, what I'm going to do is I'm going to actually add a 0 here. So instead of defining it like kds plus kp, I can also change it into the root locus notation, where I can see that I have a 0. I'm going to add the 0 to the system. And then once I've added this 0 to the system, I can go ahead and design a P-type controller. So that's basically a different approach here. Now, my advice is to use always this form if you're using the algebraic methods, because this will end up in linear coefficients. But here we have multiplications of k and z, and if there are more unknowns, this will be a bigger nightmare in this case. So if you're looking for the root locus and if you're trying to comment on your controller, then this form in line 17 helps you out even more, because you know where to place the 0. And if you have a 0 and all the poles and zeros of the open loop system GSS, then you can plot a root locus plot, and then you can choose your k and see what really is going on. So, but in order to demonstrate the bad choice here, let's define k and z. So we have k, and we can also define z because we don't know where to place the 0. That's actually the question. If you know where the 0 is, then you know one of the controller parameters. So I can conclude that z is real because we have a first order polynomial and its coefficients should be real. And this also is a coefficient, therefore it should be real. Now I have this controller. I get the closed loop transfer function, and I'm interested in the characteristic polynomial. Now let's also take this part here and display what the result looks like, or what our design problem is going to be. So now, if you remember, we had a limitation here, and the limitation was to choose 1.182 omega n equals 4. We didn't have this left part here. And I've told you that we are not going to be able to choose the settling time or omega n value different than this equation solution. But now we can choose a different value by choosing k. And since I have an additional parameter z, I can also change and satisfy this equation. And in fact, for this problem, I have two equations, two meaningful equations, but omega n, k, and z are unknown. So I have 3 parameters and 2 equations, which means that I have infinitely amount of solutions. I can choose omega n. If I'm going to choose omega n, then I'll end up with one unique solution. But in this case, I have infinitely amount of solutions. There are infinite possibilities here. So let's, for the sake of simplicity, let MATLAB decide what the solution should be. But this is going to be a bad idea because we are not choosing it ourselves. We are letting MATLAB determine our coefficients, which is not a good idea. What we should really do is we should go ahead and choose a settling time, for example, or omega n, and then try to come up with a controller. But we'll see. So now it came up with 4 different solutions. And if I look it up, it looks pretty ugly. Let's convert it into double. So kval is equal to double sol.k. We have also z. So zval, omega n val, omega n. There we go. Now let's see what kval looks like. Let's see what omega n val looks like. Of course, we have to eliminate the negative one here. And we have zval, which is equal to these. So let's eliminate some omega n values here. So omega n val should be greater than 0. Therefore, omega val should be equal to omega val index. Z and k val should also be the same. There we go. Omega n val. So we have k val and z vals. What we can do is we can just choose one of the solutions and look what it looks like. So let me actually take this part here and go ahead and do the following. So yeah, let's not change it. So for 1 equals the length of, for example, kval, I'm going to determine how many solutions there are. And for each solution, I'm going to define my Pd controller here. So I know that I should choose kval I, the ith element of that, and also zval, the ith element here. So note that I'm using 1 and zval here because it is s plus z, and divide by 1 gives me basically the Pd type controller. So instead of using k, I'm going to use fs. And let's also change the figure number to the ith here so that each solution is on a separate figure. So now I guess we should be good to go. But in this case, we might need omega n val I. Zeta is again the same. Seems to be right. So that's one. That's another one. And another one. Of course, you can immediately see that the root locus plot is not accurate here because we've added a 0 to the loop transfer function here, but I didn't reflect that on the root locus here. So what I should do is I should multiply this with the 0 because I've added the 0. Now, of course, you can go ahead and plot the root locus of fs times gs because that's also possible. But instead of that, I will leave the gain part out because if you click on the root locus for MATLAB, you will end up in the same kval as you should be. But if you include kval here, then you should look for gain equals 1. So therefore, I'm going to just include the dynamic parts of the controller, not the gain. So I'm adding all the poles and zeros of the controller to the root locus. So let's say zval I, and not kval, because that will be chosen by clicking on the root locus here. Comma 1. Now we can see that our closed loop poles are exactly on the root locus plot, and we've also added a 0 here. This means that we've basically updated our root locus by adding a 0, which is expected because it had only 2 poles, and a root locus based on 2 poles is different than a root locus based on the 0 and 2 poles. So we did change the root locus plot by adding a 0, and we've chosen exactly this point, which should be the k value here for this solution. So gain is equal to 0.42 in this case. We have another solution where we can see that for this solution here, we have points that are not on the root locus plot here, but we didn't check the negative root locus in this case. So we may have to update figure 2 here. And on figure 3, again, we have updated the root locus plot here. So let me zoom out a little bit. And we can again see that they are on the root locus here. And figure 1 and 3, if we compare them, we can see that they have different, slightly different overshoot values, but they are not exactly equal to 10. And the reason behind that is probably the 0 that is added here, because we have a dominance factor here. But for the P-type controller, we didn't have to talk about dominance because there are only 2 poles. They were always dominant. Now we have 2 poles and a 0, so the poles should be dominant compared to the 0. And if that's not the case or not dominant enough, then we will have some deviation in our requirements. And that's exactly the case here. So for figure 2, let me again check for the positivity of kval. If kval I is positive, then I should plot the positive root locus. If that's not the case, I'm choosing a negative value, then I should be on the negative root locus, which I can plot by using a negative sign here. So if I run it again, this time, For figure 2, I can see it works, and for figure 1 and 3, that's also the case. So from here, I can see that choosing different omega n values in this case, because 195 is this solution here, 8.59 is omega n in this solution, and 4.81 is the omega n value for this solution. Of course, I did let MATLAB decide what the omega n value should be, but we can choose our own omega n value, which means that using a P-type controller, we can only meet the requirement of overshoot, and we can only decide on overshoot. But with a Pd type controller, we have more control, we have more degree of freedom, therefore we can decide on more things here. For example, we can choose a overshoot and settling time. Of course, not entirely, we are not entirely free on our choice, because we want to keep the zero a little bit away or further away, because we have to have dominance factor maximized in order to be able to use the formulas that we use. So therefore, that's a limitation. But other than that, we can choose the settling time for this Pd type controller. Now, bu mu? Figür 2 mi? Çünkü negatif kök eğrisi kullanıyor ve aşım değeri oldukça yüksek. O yüzden aslında bunu ters düşün. Yukarı çok çıkmış, aşağı inmiş şeklinde düşünebilirsin. Ama negatif olduğu için ters tarafa gitmiş. Bu aşım açısından da zaten tutan bir kontrolör değil. Çünkü negatif root 9, 0 zaten sağ tarafta köklere göre. Yani baskınlık diye bir şey kalmamış zaten. Now, why does figure 2 look like this? Well, first of all, we have a negative k value, and second of all, the 0 is dominant here in this case and almost near the origin. This is not a good strategy, and we can also see that a high overshoot value is present there. So it's really a bad choice in this case. But we can work with these two here because they seem to be at least working. And this one is even better here because 11% overshoot and 15% overshoot here. So also, this was possible due to the fact that we had a term here. Now, if we look at the denominator here, we can see that we are affecting the constant term and the S term, which was not valid for the P-type controller. For the P-type controller, we could only affect the constant term here. So that's fairly important. Now, we have looked at the P controller, Pd type controller. Let's also look at the Pi type controller. Now, therefore, I might again copy a bit from here and even here. So, okay. Now the Pi type controller is defined like the following. So this is the P-type controller plus the integral Ki times integral E dt. Now again, in the Laplace transform, I can immediately see that this would be, so let's use this, Kp times E plus Ki times E divided by S, because dividing by S is integral, multiplying with S is derivative effect. So now I can also factor this one out. Kp plus Ki divided by S. There we go. Now again, the controller transfer function in this case looks like Kp plus Ki divided by S. So that's the important part. Now again, we have different notations. What we can do is we can basically write this like Kps plus Ki divided by S. This is basically the same, but this can show me that I have basically a Pd part here in this Pi controller, and I'm dividing by S. So the root locus notation or the pole zero notation can also be used for the PI controller, with only one difference being that we should divide by s. Now, in terms of the root locus, I can see that I'm adding a s term, so I'm adding a pole here at the origin, and I'm adding a 0. So designing a PI controller corresponds to adding a 0 and a pole at the origin, but the location of the 0 needs to be determined. And then once I've done that, I'm choosing a P-type controller. So therefore, I'm again going to use K and Z, but never do this if you're using the algebraic method. I'm just showing you this. Instead, you should define KP and KI and define your transfer function like that for the controller. But I'm going to be a bad example for this. Now, let's calculate the closed loop here. And let's look at the denominator. Now, since we've added a pole, since the controller transfer function has a pole on its own, we can see that the closed loop characteristic polynomial is a third order polynomial. But designing a P-type controller or Pd type controller, it was fairly simpler because of the fact that the characteristic polynomial was a second order polynomial. Now we have to take care of the third pole, and we have also a 0. We should also take care of that. So designing a PI type controller is not easier than designing a PD type controller or even a P type controller. It's a bit more difficult because we have to keep 1 0 and 1 pole out of the dominant region in order to be able to use the settling time, rise time, overshoot formulas that we have. So this means that during the design of this, I need also to define another pole. And that would be the residue pole here. And our problem, let me take this part here, or even this part here. Now, our problem is we have this denominator part. Now I have to add in my residue polynomial, and the problem, the design problem for this controller looks like this. Now we have more equations. We have exactly 3 equations in this case. We don't know what P should be, omega n should be, K should be, and Z should be. So we have 4 unknown parameters, but we have 3 equations, which is again the case as in the PD type controller. Namely, we have infinitely amount of solutions or possibilities. So we can decide on the settling time again, or we might let MATLAB solve it. So let's see what happens if we try to do that. So K val, Z val, omega n val. Now in this case, MATLAB does not succeed because we can see that Z val and omega n val is equal to 0. So the strategy here for MATLAB is to equate some of the parameters to 0 if it's possible, because it needs to reduce down the number of parameters or unknowns. So therefore, we cannot use MATLAB in this case. We should also not use MATLAB, even for the PD type controller. But since this is more of an introductory level, I did leave it to MATLAB. So here we have to now choose a certain settling time, for example. So let's go ahead and do that. Instead of having a symbolic omega n value, what will take place is I'm going to choose a certain settling time, let's say 4. And then omega n can be calculated by using the formula for settling time. So 4 divided by omega n times theta was the actual formula here. Since here we have calculated the zeta value, I know the settling time, I'm going to be able to calculate what omega n should be. So therefore, I'm going to be able to determine the exact location of the dominant complex conjugate pair. But I'm going to add P. I don't know what K and Z should look like, but there will be 3 equations and 3 unknowns and a unique solution, hopefully. So omega n, let's see. Of course, the solution has not does not include a omega n here, so therefore let's have P here and P val. So now from here, I can see that I've made a good choice due to the fact that P here is equal to 2. Now, this is important because for closed loop stability, I need to have a positive zeta value, a positive omega n value, and a positive P value. Because by definition, if zeta and omega n is positive, the real part of my solution for the dominant pair, minus zeta times omega n, and then plus minus j times imaginary part. Let's also write it down, 1 minus zeta squared times omega n. This is the solution. And if zeta and omega n are both positive and real, then my solution will be in the left half plane in the AS domain. So these are stable poles for real and positive values for zeta and omega n. Of course, they should be strictly positive. Now, since I'm multiplying this desired or dominant pole pair with a raised polynomial, I need to have also a stable PES. So the definition of PES is quite straightforward. It is S plus P. For positive P values and strictly positive P values, real P values, I'll end up in the left half plane again. So therefore, I should check for P. Now, it could be the case that P is negative, which would mean that the closed loop is unstable. And that's basically determined by the settling time choice here. So it seems like choosing 4 is good. So let me comment it out. Let's try 1, for example. Now here you can see for settling time 1, I need to have P equals minus 4, a negative value, which means that in the closed loop, I will have the dominant pole pair, but a pole at minus 4, S equals 4 on the right half plane. So this would end up in a unstable closed loop, which is not desirable. So therefore, the choice of settling time, of course, is important. And being a bit slow here might help us out for this system, which does. Now, P will be equal to 2. Since I know that P is equal to 2, 4 plus 2.86 should give me 6.862. And then minus 4 divided by 4 should give me K. I know what K and P are. I can determine what Z should be. So at this point, I should have K val, Z val, and P val. There we go. Now, I know what the controller parameters are because the controller parameters were K and Z. So therefore, I can go ahead and define my PI controller. So 1 times Z val, or 1 and Z val, so S plus Z val. K val is the coefficient here, but I have a pole at the origin, 1 and 0, because S plus 0. So I have this, so I can go ahead and copy this whole part here and paste it in here. So since I have defined my controller, I have my closed loop, but I should use Fs times Gs. And then we look for the step response. Now here, we did not plot the zeros, so let's also fix that. There we go. Let's choose a circle marker here. Let's comment this one out. Now, of course, we don't have omega n val. We did choose omega n here. Omega n is 1.69. So what else? Now here, somewhere we have the root locus, exactly here. As it was the case for the Pde Type Controller, I have to add the dynamic parts of the controller to the root locus here. So therefore, I need to multiply this with the following transfer function. Now my 0 is at Z-val, and I have a pole at the origin. They should appear on the root locus, so you should check out if they're there. So looking at this root locus, we should be able to see the following. Let's close them down. Let's close this down, and this is the solution that we are looking at. Now, a big difference is the following. We have basically reference tracking here. There's 0 steady state error because it is settling down to 1. And if you increase the time, you will see that this will eventually become equals 1. And in the root locus plot here, what we can see is that we have, again, omega n and z. They coincide at this exact point. The omega n value is 169. Zeta is, again, the same value. But we have also something here. We have the 0 and the pole on top of each other. And we've seen that actually here. Z-val is equal to 2. So let me write it again. And we have p-val equals 2. So there's a pole 0 cancellation in this case. The 0 that we've placed is basically canceled out with a pole. Now, this doesn't have to be like this. If we, for example, change, again, the settling time a little bit, so let's increase it. Let's have 5 seconds of settling time. Here we can see that now we don't have a pole 0 cancellation because it is not obligatory. So we don't have to have a pole 0 cancellation. That was just due to the fact that the real part should be equal to 2. And that's just a special case for this system here, for the settling time value 4. Now here we can see that there's a pole 0 here, and our pole pair is dominant. Now, how dominant it is determines the value overshoot here and the settling time, of course, here. Now we've chosen 5 seconds of settling time. So let's see. It seems like our settling time is 4.43, something like this. So we can check the step info here. Info, if it's there, it is. And 4.41 is the settling time value. And overshoot is approximately 6. So the dominant the poles are, the better the results will be. Now, of course, we can see that there is a low dominance factor here because we are at -2 something here for the pole at 0, whereas our real value here is, what is it again? Almost equal to 1. So there's not that much dominance factor going on here. But ideally, we want to have a further pole and 0 pair here. But for this settling time, it seems like this is not really possible. So if we increase the settling time a little bit more, let's have a dramatic change here and see if it's going to be the case. Now you can see that decreasing the speed too much does not help us out here. Of course, we can see that the pole is further on the left, but the 0 is not even on the left half plane anymore. It's on the right half plane. Now, having a 0 on the right half plane here is not that problematic, as you can see, because it does not cause instability. It's still stable here. But we can see that there's a undershoot here. So that's not really what we are looking for in our design. And we will be talking about this in the upcoming weeks. So therefore, we need a certain settling time that's not too slow, even though you want to increase the dominance factor here. This is not a good choice. And you can also see that the overshoot value and the settling time are not really exactly the values that we are looking for, because it is approximately 15.19. In terms of settling time, it seems to be good, but overshoot is 13.5. Why do I have to choose this? whereas 4, for example, is ideally the best solution here. Of course, that's not always the case for the Pdi type controller. For this problem, we've only defined the overshoot value, and we've chosen the settling time on our own. Therefore, we have the liberty here to try to choose the settling time. But most of the time, that's not the case. You're given the specific requirements, and you're looking for the controller. Yeah, of course, we have infinitely amount of solutions in this case, so there should be a better way for trying to come up with a controller, because eyeballing it is not the best approach for controller design, and that will be covered in the next lesson or lecture for the laboratory, which I'm going to be, by the way, preparing for you online, because we have an exam next week. So next week there will be no laboratory, so I'll be uploading it maybe in 1 or 2 days from now. So let's quickly check the PDF and conclude our today's discussion. So what did we learn in this laboratory session here? Well, we've seen that there is a Pd type controller or Pi type controller that can be designed for the same requirements. We've chosen the P type controller for A, and we've seen that we can only determine the overshoot here. We cannot touch the settling time of the system because of the root locus. You can check the root locus here. Let me see if I have it here. Again, we can see the root locus here, and we can see that we are not able to change the real value of the pole pair. So if you cannot change the real value of the pole pair, you cannot change the settling time. The only thing that you can decide is the slope of this zeta here, the zeta line here, which will directly change the zeta value or the overshoot. Now, using a Pd type controller has more control over it. You can think about this as choosing a 0 for, or adding a 0 to the root locus, which is basically manipulating the root locus plot. And once we've manipulated it so that we can end up in a solution that has a different settling time value, we can then choose the P-type controller part. So we have different scenarios as shown here. And we've also seen that the Pi controller is somewhat similar to the Pd type controller, but with an additional pole at the origin. But this exact difference here is also the difference for reference tracking. So if you add a integrator, 1 divided by s is an integrator, or a pole at the origin to the system, then you can track reference type references perfectly. Now, if you're trying to track step type inputs, then 1 pole at the origin is sufficient. But if you want to, for example, track ramp type inputs, then you might need to add another one. So yeah. And we've designed a Pi type controller, but we've seen that trying to design a Pi type controller is a more difficult task than a Pd type controller or P type controller, but it has its advantages. Now, there's also a comparison here. You can see that the only controller that ends up in reference tracking is the Pi type controller, whereas you can choose P-type controllers and Pd type controllers, but they don't guarantee reference tracking in this case. So, of course, Pd type controllers are more of a stability controller. So, for stability examination, a P-type controller seems to be the perfect fit. But if you need to track step-type inputs, then you need an integrator. So, Pi-type controllers and maybe Pid type controllers are a good candidate for that. Not the Pd type controller itself, for example, because it does not have an integrator. So that's pretty much it for this week. If you have any questions, I might try my best to explain it to you. In the PDF, you can see step-by-step the solutions here. As I've mentioned before, I'm going to upload week 5 as soon as possible. So there will be no online session for week 5. You will have it available. The only difference in week 5 will be that there will be a design method rather than eyeballing it or trying to come up with a settling time. We will try to design better PID type controllers. So that's it for this week. See you next lesson.